this video, we'll talk about graphs, graphing functions, and how we can read graphs simply and how we can guess their form and whatnot. So a graph is a diagram that illustrates the relationship between your function and its variables. Common graph types are polynomials of quadratic and cubic functions. So like quadratic function would be like x squared plus something x plus c. Cubic would be, as you could guess, and would just be x squared or one value of x rather than three. A line, as we have pointed out, for linear functions just has one value of x. And then similarly, we have the root functions, exponential, and logarithmic functions. So all of these types of graphs are useful to identify, and you should get some practice with for sure. So without further ado, let's get some practice. So the cubic and quadratic polynomial go like this. Like I pointed out, quadratic would be like x squared plus yada, 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 and cubic would be like x cubed plus yada, yada, yada. Anything of the form of x squared has this parabolic arc to it, which goes like that, almost like all the time, everywhere. Anything that comes up after the x squared is something that shifts or bends or warps this picture, but it's good to know what the first general picture looks like so that whenever you're asked to graph something that is a little bit more like, what's x squared plus 1, then you would be like, okay, well, I know that x squared looks like this. And I know if it's plus 1, then that means all the y values get increased by 1. So I would start the graph from here and then do that graph. You know what I mean? So the purpose of this video is to have yourself be familiar with the standard forms of these graphs so that you can manipulate them later. So x squared, things that are squared, as we know, are always positive. That's why this function is always going upward in a positive direction, because even if you threw a negative x in there, it ends up being positive. However, for cubic polynomials, since it's cubed and not squared, that means that we can have negative numbers when we do put in negative numbers. That means on the positive side of the x-axis is going to go up with this parabolic arc, and on the negative side, it's going to go down with this parabolic arc. Another quick examples would be like a line graph and like an absolute value graph. So similarly with the quadratic and cubic functions, the absolute value implies that any value of x you plug in to x is going to be positive. So you pretty much just have a straight line going in the positive direction in x and a straight line going in the positive direction in negative x. So you have basically this sharp V type of graph where everything is like a 1-to-1 ratio for positive things. So, x4 is going to equal y at x4, y equals 4, and at x negative 4, y still equals 4. If we have a straight line graph where this value can be negative, then the relationship is 1-to-1, where instead of it being negative to positive, it's just positive, positive, negative, negative. So if I have x at x equals 3, y equals 3, and at x equals negative 3, y equals negative 3, because I have just a straight line that splits the two planar regions down the middle. And I'm sure you've seen some examples of these graphs before, so hopefully this makes a little bit of sense, or some change, some dollars. All right, so graphs that are a little bit harder to memorize, but are equally important to, are some like reciprocal graphs, logarithmic graphs, and root graphs, which are going to be the next things that we talk about. A reciprocal graph would be like, instead of y equals x, I would have y equals 1 over x. Since I have x in the denominator, and we know that 0 can never be in the denominator or else we get an undefined term, then I have something called an asymptote, at x equals 0, an infinite asymptote that goes on forever, where this function will never touch 0, and this function over here will never touch 0, because again, for anything with like an x in the denominator, we can never have 0 in the denominator. That's just not something that is allowed in math. So that's where our asymptotic behavior comes from. And for the same reasons, this is the last couple slides, when it's just one value of x, that allows us to have positive and negative values. So I would have this shape over here on the positive side and this shape over here on the negative side. Whereas if it was x squared, I would have that shape both be on the positive y-axis. So looking at some square root and cube root graphs, square root graphs look very much kind of like a quadratic parabola. However, since it is a square root and we know that they can't be negative, I don't have this extending into any sort of negative space. It can't do that because that's not technically a function when it does that. So all I really have is like one part of the parabola going off like this way. Again, for the same reasons in the last few slides, if I have a cube root, cube roots can be negative. So when I do pick negative values, I pretty much have this shape again, but now it's extended into the negative y plane where it's just mirrored across to the y-axis. It's good to have yourself be familiar with these types of functions, because I'm sure you'll come across times where you'll be asked to graph something that has a root in it, and it would look something like this. All right, I think wrapping up, we have exponential functions and logarithmic functions. Exponential functions can take any value, negative or positive, but can't cross the x-axis because the y value here will never be 0 or never be negative. We can think about this as like this. So like e to the x, if I plug in any positive value of x, I'm still going to get a positive number. But if I plug in any negative value of x, like what happens? Like I have e to the negative x. But as we've pointed out a few times, anytime you have a negative in the exponent, this is just simply 1 over e to the x, which still gives me a positive number. So as x approaches negative infinity, this function approaches 0. And as x approaches infinity, this function approaches infinity. Have a similar type of relationship for the logarithmic function or the natural log function. There's two important things you got to remember. Log of 1 is always 0. So right here, this proves it right there. The y value when x is equal to 1 is 0. So this makes sense. You can pick numbers between 0 and 1 and get negative values for y. So that's why this extends into the negative space. However, for a similar reason, you can't pick negative x values because then you would get an undefined logarithmic function. So this is what the general form for like a log function would look like. Again, the goal here was to introduce you to all the different forms of the graphs, so that when you're asked later in exams or homeworks, that if you're asked to, graph x squared minus 5, or, absolute value of x plus 5 or something like that, that you can go look at these standard forms of the graph and be able to make slight adjustments to whatever else is being added in there to get the correct form for the graph. So I hope this has been helpful for you. And of course, there's always online references and notes that you can look up if you ever need any help or assistance in the future.